Hello everyone, I'm J Wildberger. In this lecture we're going to be looking at roots of complex numbers. So this is touching base with a very rich theory of polynomials and their solutions when we go to the complex plane. We get a richer and more satisfying picture to the algebra of polynomials. So a good place to start is with the simpler story of finding roots of complex numbers. What do we mean by that? We mean solving an equation, that looks like this. That looks like z to the, say, n equals some complex number w. So w is a complex number, and we want to find solutions of this equation, z to the n equals w. And typically, n is a natural number. So that is a much richer story than it is over the usual number line, over the so-called real numbers. And it will turn out that typically we get actually n distinct solutions to such an equation. And a good place to start is with a very special but important case when the w is actually 1. So the special case is when we're considering equations of the form z to the n equals 1. Solutions of this equation are called roots of unity. Solutions are more precisely nth roots of unity. Nth roots of unity, unity being 1. Okay, so let's have a look at this equation for simple values of n. That's an instructive place to start. So when n equals 1, well, then it's a pretty simple equation, z equals 1, and there's only one solution to that, which is z equals 1. So on the complex plane, I might actually draw our unit circle, which we like a lot, okay? And so the solution here is just considering just that point there. Okay, how about when n equals 2? So now we're talking about z squared equals 1. Okay, there's two solutions to that, and they are z equals plus or minus 1. And a reason why we can see that is because z squared minus 1, when we bring everything to one side, that factors as z plus 1 times z minus 1. Okay, so it's really the factorization of this into these linear factors that gives us the roots or the zeros. And there are two of them in this case, plus and minus 1. So if we drew a picture, maybe I'll draw it up here. The picture for this second case would be, there's this one and this one. Okay, how about when n equals 3? Now we're talking about z cubed equals 1. Now, that's a little bit trickier. So how would we solve that? Well, if we wanted to look at the high school kind of approach, we might think about trying to factor it. And one factor is pretty easy. We can extract a z minus 1 from that. And then the remaining factor is z squared plus z plus 1. Okay, which you can verify by just expanding out. And it's kind of obvious that z minus 1 is a factor because obviously this thing here has a 0 of 1. So z minus 1 is a factor, but there's this additional quadratic factor. So to find the other solutions to this thing, what we should do is we should try to see when this second quadratic factor is also 0. So let's solve this quadratic equation, z squared plus z plus 1 equals 0. Okay, so that's a quadratic equation. We know that, well, ordinary quadratic equations have the quadratic formula recipe for solutions. And in fact, sort of algebraically, that works with complex numbers too, subject to a particular little issue, which we'll see in a second. Okay, so let's apply the quadratic formula. What would that tell us? It would say that z is going to be equal to, so minus b, so that's, I guess, a minus 1, and then plus or minus square root of b squared, okay, 1, minus 4ac, so that's about minus 4. all over 2. And what is that? Well, that's equal to minus 1 plus or minus the square root of minus 3 over 2. So to find a solution to this, we need a square root of minus 3. Now, in high school, there is no such number, and we would say that this quadratic equation doesn't have a solution. But in the complex plane, we have a little bit more flexibility because we have I, and we know that I squared is equal to minus 1. So we can interpret this square root of minus 3 to be I times the square root of 3, or minus I times the square root of 3. So if we have a square root of 3, like a real number, then we multiply that by I, or by minus I, and we square that, then we're going to get minus 3. Okay, so there's two solutions here. So to come back to our equation here, we could write this now as minus 1 plus or minus I times root 3 on 2. Okay, so where are those numbers? Now let's have a look at then the 3 cubed roots of unity. Okay, there's 1, there's I. So one solution is this one here, which is 1. And another solution is right here, okay, where we have to go minus a half. That's minus a half there. And up root 3 on 2, I. And so this is minus 1 plus I root 3 all over 2. And the other one, where we have a minus sign, rather, is down here. So that'll be minus 1 minus I root 3 on 2. And we know from our familiar experience with trig things that we have a situation here where there's a kind of a 60 degrees. This is 60 degrees, or pi by 3. So this is really a third of the way around. So this is 2 pi on 3. And this is also 2 pi on 3, and this is also 2 pi on 3. In other words, these 3 points that we have make a nice equilateral triangle, which is embedded in this circle. Okay, so finding the 3 roots, 3 third roots of unity is essentially geometrically same as finding this equilateral triangle in the unit circle where one of the vertices is 1. So to summarize what we've done, we have found therefore that the solutions to z cubed equals 1 are, okay, there's z equals 1, there's z equals minus 1 plus I root 3 on 2, and there's z equals minus 1 minus I root 3 on 2. And these form an equilateral triangle in the unit circle. Excellent. Okay, great. So what about the next one? Let's go to n equals 4. Now we're talking about z to the 4 minus 1. Well, we could start by factoring that. That's a difference of squares, so it'll be z squared plus 1 times z squared minus 1. And, okay, can we factor that? Well, one of the factors is easy to factor. We get z minus 1 times z plus 1. And in high school, you wouldn't be able to factor the z squared plus 1 because it doesn't have any zeros in the real numbers. But with the complex numbers, we can factor that because this is looking for solutions of z squared equals minus 1. And we know the solutions are I and minus I. So we can, in fact, factor this as z minus I, z plus I, z minus 1, z plus 1. And so the fourth roots of unity are z equals, I'll just lift them 1, minus 1, I, and minus I. And geometrically, that's a very nice situation. One of them is there. That's 1, and then I is up here, and minus 1 is here, and minus I is down here. So again, we are getting a nice regular polygon, in this case a square, inscribed in the unit circle. Okay, so that's great. So we can kind of perhaps expect that something like that is going to happen for higher powers, and that's exactly what happens. In general, the solutions to z to the n equals 1 form a regular n-gon on the unit circle. And way to see that is to let's let z be, say, r e to the I theta. That's a general polar form for a complex number. And we'll stick that into the equation. Then we get r times e to the I theta to the nth power equals 1. Okay, so what does that amount to? Okay, so or this is r to the n times e to the I n theta equals 1. Now, what's the polar form for 1? Well, 1 is, if we write it in polar form, it's 1 times e to the I times 0, really, right? Because the angle is 0, the argument is 0. So if we compare these two sides of the equation here, we kind of get two equations. One of them is that r to the n equals 1, and the other one is that e to the I n theta equals 0. Okay, what are the solutions to that? Well, r is a positive number, a real number, so there's only one solution to that. R has to be equal to 1. And what about e to the I n theta equals 0? Well, from here, let me go e to the I n theta. That would suggest that n times theta is equal to either 0 or maybe 2 pi or maybe 4 pi, etc. Okay? And a way to get all of those possibilities at the same time is to write it rather as n times theta equals 2 pi k for some integer, actually, not just a natural number, integer k, so in z. Okay, so that is the requirement. Remember that the exponential has a periodic aspect. If we increase the argument by 2 pi, then we go back to where we're starting because we're going around the unit circle. So this second equation here will be valid when n theta is some multiple of 2 pi. Okay, and that tells us then that theta is going to be 2 pi over n times k. In other words, a multiple of 2 pi over n. So when we put all of that together, what do we see? We end up with a situation where we have z having to be on this unit circle, and one solution would be z is e to the I 2 pi on n. Another solution, well, actually one solution would be this one. That's actually the simplest one. That's e to the I 0. 0 times 2 pi on n. Okay, and then we have this one. And then the next one over would be e to the I 4 pi on n, twice the argument of this one, going the same angle. And then the next one would be e to the I 6 pi on n. And we go around like this, and there's going to be altogether n solutions, because each one of these angles is 2 pi over n. 2 pi over n. 2 pi over n. So the last one will be e to the I 2 pi over n times n minus 1. After that, we're back to this one here. So this is the same as e to the I 2 pi over n times n. Okay, we get back to where we started. So we end up getting an n-gon, a lot of equally spaced points all the way around, making a regular n-gon. So this entire problem connects with a very old and famous problem of sort of how to construct a regular n-gon. Okay, so that geometrical problem is intimately connected with this arithmetical one, or algebraic one, when we're talking about complex numbers. So I want to show you, just change gears here a little bit, what happens here in the unit circle. I'm going to illustrate things with GeoGebra. So I have the unit circle here, and I've started with this point Z1, okay? And maybe just make that a slightly different color so we can see it better, maybe blue. Okay, so there's Z1. Now, what we see here, in addition to that one, is all kinds of... Sorry about that. Okay, there we go. So if there's Z1, then this Z2 is Z1 squared. It's the square, and then this is the cube, and then this is the fourth power. So these are successive powers of this Z1. And here are negative powers. So here is Z1 to the minus 1, Z1 to the minus 2, and so on. So I want you to have a look at what happens to these powers as I move Z1 around. One of the beautiful things about GeoGebra is we're allowed to do this, and it will just move everything accordingly. So notice that these positive powers are just marching around, okay? So, whoops, okay. So suppose that I brought it all the way up to here. So just Z1 is now at I. What's happened is that all those higher powers and the negative powers also, they all coincide with these fourth roots of unity. So this is Z1, this is Z1 squared, this is Z1 cubed, Z1 to the fourth, Z1 to the fifth, Z1 to the sixth, and so on. And going backwards, this is 1, this is Z1 to the minus 1, this is Z1 to the minus 2, and so on. Now if I carry on a little bit, say move it close to about 120 degrees, then there we go. We see the 3 third roots of unity appearing. So all the successive powers are rotating around in this triangular fashion. And, whoops, we could, sorry, let's go back. Another kind of interesting case is there's at some point here I should get a regular 5 gone. So right there, you can see that we have 5 points. So this is the story of the 5th roots of unity, which is a little bit algebraically more tricky to establish. So let's have a look at that. It's actually quite an interesting situation. Okay, so let's now go back to our screen here. Okay, so now let's have a look at n equals 5. Where we're talking about the solutions of z to the 5th equals 1. So if we want to factor this, the way we do that is we take z minus 1, and then we get, say, z to the 4th plus z cubed plus z squared plus z plus 1. Now, factoring this quartic is, let's say, a little bit trickier. So here is one way of thinking about that. So if we take z to the 4th plus z cubed plus z squared plus z plus 1, here's a little bit of a trick. If we write this as z squared plus 1/2 z plus 1 all squared, if you square this thing here, you'll see you get almost this thing. You just have to make a little compensation. You have to actually put in -5/4 of z squared to make everything equal. So you can check this, all right? You can check this little identity. And once you've done that, you see that what you have on the right-hand side is a difference of squares. So it's a difference of squares. That means we can write it as product of two linear factors. And what are those linear factors going to be? Well, it's going to be this first one plus the square root of this thing, and then the other one is going to be this first one minus the square root of this thing. So we write down those linear factors, and we're going to get z squared plus 1 minus root 5 on 2 times z plus 1. And the other one is going to be z squared plus 1 plus root 5 on 2 times z plus 1. So we get a kind of a non-obvious factoring of this quartic into these two quadratic factors, but the quadratic factors themselves have these square root of 5s in them. Okay, so that means that if we want to completely factor this thing out, well, then we would have to essentially apply the quadratic equation to both of these quadratic factors. And we could do that, and I'm going to leave that as an exercise. And what do we end up getting? So we get the 5th roots of 1. I'm going to show you the picture. Okay, so here is our unit circle. And, okay, there's one here, there's one here, there's one here, there's one here. And altogether, these should form a regular pentagon. Okay, regular pentagon. And it's a little bit complicated what the actual points are here, but let me write down what they are. Okay, so this one here turns out to be root 5 minus 1 over 4, that's the real part, plus the square root of 10 plus 2 root 5 inside the bigger square root, all over 4, times I. And this one down here, well, it's going to be the complex conjugate, okay? If that's z, then this one here is going to be z bar. You'd obtain that one just by changing this plus sign in here to a minus sign. And what about this one over here? Well, it's similar, but a little bit different. It's minus root 5 minus 1 over 4 plus square root of 10 minus 2 root 5 over 4 times I. And this one here is the complex conjugate of that. And these are the solutions that you get by solving the two quadratic equations that are appearing here. And once you have done this, then what we get is as a consequence, we find the values of cosine of 2 pi on 5, right? This angle here is 2 pi on 5. And so the x-coordinate, this thing here, is going to be cosine of 2 pi on 5. And the y-coordinate is going to be sine of 2 pi on 5. That's going to be that thing there. And of course, we could also go a little bit further, and if we wanted to find this angle here, that's going to be 4 pi on 5. So we could also get values of cosine of 4 pi on 5 and sine of 4 pi on 5. From these, they're going to be these values here and here. Now, this is very explicit. This is in Cartesian coordinates. We've used some algebraic trickery in order to factor these things. From the point of view of complex numbers, another way of describing these things is in terms of polar coordinates. And basically, in other words, we can connect now with the previous formula where I told you in general what you get up here. The general formula will be in terms of multiples of 2 pi over 5. So maybe I'll do it in a different color. How about blue? Okay. So this number here has an alternate expression as e to the I 2 pi on 5, because that's the argument right there. So that's e to the I 2 pi on 5. And this one here is e to the I 4 pi on 5. And this one here is, well, e to the minus I 2 pi on 5. And this one here is e to the minus I 4 pi on 5. So that's another way of describing these fifth roots of 1. Okay, so once we have this sort of technology in place, then actually we can extend this to get nth roots of more general complex numbers. Okay, so suppose now we want to solve, let's say, solve z cubed equals 5i. Okay, so here's our unit circle, 1i, and up here somewhere is 5i, all right? And now we want to find complex numbers whose cube is this 0.5i. So now we're looking for a point z whose cube is equal to this 0.5i up here, but we're no longer on the unit circle, so we have to be a little bit more general. So to prepare us for that, let's have another look at GeoGebra. Here, I remind you, there's the point z1, and here are the various powers. Now, I'm going to disassociate the point from the circle. Now, have a look at what happens to the powers. So they still march around at an angular, regular fashion, but their moduli are increasing. And that's because the modulus of the square is the square of the modulus. So if this thing here has modulus, say, 1.1, then this next power will have modulus 1.1 squared, and this will have modulus 1.1 cubed. And the inverse will have modulus 1 over 1.1, and this will have modulus 1 over 1.1 squared, and so on. And that becomes, of course, more extreme as we get further and further from the unit circle. So if we make everything a bit smaller so we can see more clearly. Okay, so actually let's see if we can find our point 5. So I'll write down 5i here somewhere, see if we can get that point, 5i. Okay, there's 5i up here, it's z12. So we're looking to put z in such a place so that this third power, z sub 3, coincides with this 0.5i. So let's see if we can just do that on the page here. Okay, I'm getting pretty close. It's not hard to do it exactly. Okay, oh, there's not bad. So here's a value of z, for which here is z squared, and here is z cubed. So this would be one, at least approximate solution to the equation z cubed equals 5i. Now, I want to show you where the other solutions are. To do that, let me draw a circle with center through point. Okay, I'm going to draw a circle now, centered here, through this point here. Okay, now I'm going to take this point z1 and I'm going to rotate it by a third of a full turn. So let's see what happens as I do that. I'm going to go around. Whoops, I have to go back. Sorry. Let's take the point. I'm going to try to move it roughly on this circle. Okay. Whoops. I'm moving it around the circle roughly. Okay, can you see? Right about now, somewhere around here, okay, it's going to be another value for which the square now is down here, and the cube is up here pretty close to 5i again. So what's going to happen is there are going to be 3 solutions, and there will be the one that I showed you first, and then there's this one over here, and there will be another solution down here, and it'll turn out that these 3 solutions themselves form a nice little equilateral triangle on this bigger circle. Okay, so let's see if we can see that algebraically. Okay, so we'll go back here, and we are going to approach this with polar coordinates. Okay, so let's use polar coordinates. So we use polar coordinates, namely, we let z be r e to the I theta. And we also write 5i also in polar coordinates. So the modulus of 5i is 5, and the angle is pi by 2. So it's e to the I pi by 2. Okay, so now we have then that z cubed equals 5i becomes the equation r e to the I theta cubed equals 5e to the I pi on 2. Or r cubed times e to the 3I theta equals 5e to the I pi on 2. So what can we deduce from that? So from that we deduce that the moduli of both sides are the same. So r cubed equals 5. And in terms of the arguments, 3 theta has to be equal to pi by 2 up to a multiple of 2 pi. And it's crucial that we allow this flexibility in the angle by introducing plus 2 pi k, where k is an integer, which we'll write like this. Okay, so there's actually quite a few possibilities encoded in this second equation. So the first equation, because r is a positive real number, has to be r equals cubed root of 5. So we write down that symbol. Of course, that's general, something that we can only calculate approximately, but nevertheless, it has a unique value. And what about theta? Well, solving for theta, we get theta equals pi over 6 plus 2 pi on 3 times k. So there are now going to be 3 solutions, because as k varies through the integers, this 2 pi on 3 will repeat itself every 2 pi whenever k goes up by 3. So we get solutions. Theta equals pi over 6. So that's when k equals 0. When k equals 1, we're going to get theta equals pi over 6 plus 2 pi on 3, which I suppose we could rewrite as, in terms of 6, that's pi over 6 plus 4 pi on 6, altogether 5 pi on 6. So that's when k equals 1. And when k equals 2, we would get pi over 6 plus 4 pi on 3, which equals, that's 8 pi on 3, so plus 1, so it's 9 pi on 6. 9 pi on 6. And that's when k equals 2. And let's just have a look what would happen if we went up to k equals 3. So for k equals 3, we would get theta equals pi over 6 plus 2 pi. Okay, but that's really the same as pi over 6. So that means we're just repeating the value that we got initially here, right? So that's what happens after every 3. We repeat the values that we already have. So we're really getting 3 solutions: pi over 6, 5 pi on 6, and 9 pi on 6. Okay, so to summarize, so therefore the solutions are z equals the cubed root of 5 times e to the I pi on 6, the cubed root of 5 times e to the I 5 pi on 6, and the cubed root of 5 times e to the I 9 pi on 6. Okay, So these could be perhaps simplified. We do know that pi over 6 is the same as 30 degrees, so we could write this in Cartesian coordinates if we wanted to, but it's kind of useful to just regard it like this. And geometrically, what are we getting? There's our unit circle. The cubed root of 5 is a little bit bigger than 1, but not as big as 2. So maybe here is r equals cubed root of 5. And then our 3 points are ones where the modulus is pi over 6. So that's like this one over here. Okay. And then the next one is 5 pi on 6. It's going to be something like this. And then 9 pi on 6. It's the same as 3 over 2. That's going to be actually right down here. So these are the 3 solutions to z to the cubed equals 5i geometrically. And here are the corresponding algebraic values. All right, so good. We've had a look at nth roots of unity and both a geometrical and an algebraic approach using polar coordinates and relying very much on the exponential polar form. And we've been able to extend this to taking nth roots of more general complex numbers. This is all in the direction of solving more complicated polynomial equations in the complex domain. So I'll see you next time.